Welcome. Let's start with a short question. Is the Pythagorean theorem too difficult for children? If so, why do older students still have trouble making reasonable use of the theorem? The answer is, of course, it depends on how it is taught. Let's unpack some big ideas in early mathematics and explore intellectually generative pedagogy, the importance of spatial reasoning, and the long-term goal of building a strong mathematical foundation for children, all in the context of the Pythagorean theorem. Teaching big ideas in early childhood is like laying the foundation for a skyscraper. By maintaining intellectual honesty, we ensure that as children progress, their cognitive structure is prepared to support more complex mathematical concepts later on. Pause for a moment and think about Bruner's 1960 hypothesis. Any subject can be taught effectively in some intellectually honest form to any child at any stage of development. What does it mean today in the age of artificial intelligence? Learning is a cycle involving behavior, structural brain changes, and emotional engagement. In this process, struggle is a necessary component for growth, not a barrier to success. Early educators act as mathematical surgeons, performing critical work by modeling and guiding children. Teachers are truly the enacted curriculum, building the bridge between a child's current life and advanced concepts. And they use a variety of cultural tools, actions, words, pictures, and symbols, as well as human modeling. As Rousseau noted, every piece of knowledge has a family of situations that give it meaning. In this video, we use physical, geometric models to help ground abstract ideas for young learners. For early grades, our approach focuses on visual engagement rather than complex formulas. By asking simple questions about squares, we can build essential skills in counting and shape identification. As students reach grades 2 and 3, we shift to geometry and unit measurement. We guide them to discover triangles and use unit squares to understand area through multiplication and addition. In grades 4 and 5, we introduce the coordinate plane through narrative prompts. By helping students visualize the distance between friends in a neighborhood, we set the stage for exploring right triangles. Here is the Pythagorean reveal. By imagining squares on the sides of a triangle, students can intuitively conclude the distance without needing complex algebraic notation. Abstract ideas require tangible experiences for young learners. By using 3D printed, hinged puzzles, children can physically manipulate these geometric models to see how the multiple representations connect to each other and point to a developing abstract idea about right triangles. When children can physically pull the pieces apart and rearrange them, they don't just memorize a theorem. They feel the truth of the relationship between areas in their spatial memory. Even advanced visual proofs become accessible through counting. By partitioning visual units, students can develop a deep comprehension of complex angles and symmetry. This table outlines our curricular bridge matrix. It shows how we evolve from basic counting in early grades to advanced spatial reasoning, using one consistent and intellectually unfolding model. Moving away from rote memorization, this approach allows math to be seen as a connected, lifelong tool for solving real-world problems in 3D space. The choices we make in early mathematics are critical. By building an intellectually generative foundation, we prepare children to support their own cognitive architecture for years to come. And yes, there are multiple pathways toward mathematical understanding. One way or the other, we have to engage children in making and doing mathematics, certainly not by watching a video. So this video is just an invitation.